Hello, my dear students. Welcome to the fourth class of ongoing Newtonian Mechanics for undergraduate course. In this class, we'll be discussing about velocity and acceleration in plane polar coordinates. In the first three classes, we have discussed about dimension analysis, error analysis, and a brief about simple mathematics like differentiation, integrations, and of course, vectors. So let's begin with what is plane polar coordinates. Before that, I would insist that if you're watching this video in YouTube or Facebook or somewhere else, please subscribe the course for only rupees 999 for now. Okay. So brief content of today's class. What is a plane polar coordinates? What is circular motion? What is centripetal acceleration? What is fixed point rotation about an axis? What is velocity in plane polar coordinates? What is acceleration in plane polar coordinates? And we will end up with a spatial example, which will involve a little bit of coupled differential equations. So don't worry about that. Okay, let's begin with. This topic is very important, as we have almost every year we get a question in IIT Jam. So very important. Today's class is very important. Every year we get a question in Jam, sometimes in CSI and NET, and GET. So please begin, my friends. Should I make myself a little bit bigger? No, I don't think so. It's fine. So what is a plane polar coordinates? Plane polar coordinates, I may move this coordinate please. Okay, guys. So you know about Cartesian coordinates. You divide your space by drawing lines, parallel lines, and parallel lines with perpendicular with the first parallel lines. So this is your x, this is your y. You know, in this direction you have is your x, sorry. You have your x in this direction, you have your y in this direction. So your x direction of your x is fixed, direction of your y is fixed. In plane polar coordinates, we actually, there is no fixed r and theta. See, if you have a point here, you get your r this and your theta this. I believe you know what theta is. So the main question is, here the direction of r is not fixed. A particle here, the direction of r will be this. A particle there, the direction of r will be from origin to the particle's direction. So, and the direction of theta is not also fixed. Here the direction of theta will be like this. Here the direction of theta will be like this. R and theta are always perpendicular. So please understand what your r and theta is. When r is constant and theta varies, you get a circle. Of course, r constant and theta varies. When theta constant and r varies, you get a straight line. So when I see a diagram, particle here, the direction of r is in this direction, r cap will come across. the direction of theta is this. So geometrically, your x is r cos theta. This direction is r. So sorry, this distance is r. So r is square root of x square plus y square. X is this and y is this. And theta is of course tan inverse y by x. This is simple projection, simple trigonometry. I told you in the second class a very brief outline of trigonometry. So don't worry about it. If you're not getting anything here, go to class 2, check the geometry and vectors, then come again. This is just class 10 level of geometry. So okay guys, now we properly define r cap and theta cap. Say this is your x-axis, this is your y-axis. You have a point here. So r cap is the direction, it's a unit vector in the direction of from the origin to the joining of that point, any point. And theta is a perpendicular direction drawn from positive x-axis. So this is your theta. So this is your theta. So that theta is in this direction. Okay. So the main important point is the direction of r cap and theta cap vary with position, whereas I cap and j cap have fixed direction. Okay. So please understand, if you have one point here is this, so its r and theta direction will be there. It should be, there is a printing mistake there. So this is r1, this is theta 1. Here this is r2 and this is theta 2. The angle between r and theta, that r hat and theta hat, is always 90 degrees. Your r, I and j is fixed always, but as you see, your r hat and theta hat changes. So the direction depends on the value of theta only, not on r. You understand? If you have an axis here, if this is your r hat in this direction, and if you keep increasing the direction, or come in this direction, if your theta is fixed, the value of r hat and theta hat is always fixed. So that I shouldn't put the direction there. If you have a particle here, your r hat position will be there. So this is to be understood. The r is always drawn from the origin. So okay, we have now a very simple geometry, that if you have an r hat in this direction, so you can easily check, just simple geometry is there, that your r hat will be cos theta I hat plus sine theta j hat, and your theta hat will be minus sine theta I hat plus cos theta j hat. Just keep it simple. If you have r hat here, the projection, you think about that your i's projection is here, and your j's projection, this is j's projection is here. Everything is unique. All r hat, theta hat, I hat, j hat. The magnitude of all the hats are simply 1. So we can have many different ways to understand it. Here it's a simple understanding. In this direction of r hat, you just project I hat. So I hat's projection over there, because this angle is theta, so that will be cos theta. And j hat's projection, as this is 90 minus theta, it will be sine theta. So r hat will be cos theta I hat plus sine theta j hat. And now think about theta, the direction of theta hat. Here, your i's projection will be a minus of sine, because i's projection in this direction will be sine. So this is theta. You can see that this is 90 minus theta. This will be sine theta, and it's opposite direction, so it will be minus sine theta. And the projection of j in this direction, this will be theta, so that will be cos theta. We may have a geometric argument also in a more clear sense, but this is the first step to understand the relation. You do always remember this, because this is important. So okay, let's see what we can do. So that r, which is the position vector, remains the same. Of course, this is called the position vector. In a plane polar coordinate, we write it r as xi hat plus yj hat. Sometimes I say xi cap plus yj cap. And in plane polar coordinate, I write it r as the magnitude of r multiplied by r hat. So now I tell you that xi hat plus yj hat is r cos theta I cap plus sin theta j cap. Whenever I say cap or hat, that is the same. And that r cap and theta cap, which are unit vectors along the direction of r cap and theta cap, are also written as er and e theta. So whenever you see er or e theta, you assume it's same as r cap and theta cap. So we'll go to next, circular motion. So please do understand that. What did you learn? We learn about what is a polar coordinate, what is r and what is theta, what is r cap and what is theta cap. This directions will be a unit vector here. In this direction we'll have a unit vector there. And we have a geometric argument that your r cap and theta cap will be related with I cap and j cap, just like this. If you do not understand this, don't worry, you will understand in due course of the class, or maybe after the class you please discuss with your friends and please post in the WhatsApp group that sir, I understand that at the first glance it may not be that clear. So let's see what we can do in the next part of the class. Okay guys, so we see this r will always be written as position vector. Whenever your position is, your r will be xi cap plus yj cap into the polar. This is your position vector. Position vector that dictates the particle's position, where the particle is. This is described here. It's a polar, it's a Cartesian coordinate, and this is a polar coordinate, as you may say. But I will say that this position vector itself, this r vector, does not need any spatial coordinate system to be mentioned with. That to describe a position vector, I don't need any spatial coordinate system. The position vector is a position vector in all coordinate system, whether you are using Cartesian coordinate, or you're using a polar coordinate, or you're using a spherical polar coordinate or cylindrical coordinates. In all coordinate system, the position vector is simply this r vector. It may be written in this term, may be written in another term, may be written in some another term. Always the position vector is a position vector. So and the basic definition is this: in 3 dimension there will be a z k cap will be added there. We'll come to the 3D coordinates. So okay guys, now we'll focus a bit on circular motion. So circular motion means your r is constant. Better I write it here. paste it next two slides, which will be your copy of this. So okay, here your r is constant, the particle is rotating. So at some point of time r is here, after some point of time r is there. The angle it traverses is d phi. So this is d phi. So here it's r, let's say this is, let's say, r plus delta r as a vector, r vector, r plus delta vector. So all are vectors. So the change of the vector is in this direction. And that d phi, from very simple geometry, you know that if the displacement is small, then this distance can be approximated as r d phi. This is the definition of angle actually. Whenever you did a definition of your small angle, whatever angle, so angle is this distance. If this distance is your angle, this is r theta. And when the angle is small, so that can be approximated as straight line. So we'll use this again and again every time. So here there is something like called omega. Omega is nothing but how much theta is changing with respect to time. That means, say, let's say your delta r is r delta phi, when delta phi is small, of course. So then if I divided delta r by delta t, that we got r delta phi delta t. So that delta phi delta t is defined as angular velocity, better to say as how much theta is changing with respect to time, or more precisely, in one unit time, let's say it's a second, that in 1 second, how much your theta is changing. That is omega. Omega is delta phi delta t, how much angle is traversed. And that omega is a vector. It's called an axial vector. So we'll come across some point of time, let's say, what is an axial vector? Sorry. So, okay, in a vector diagram, let's say if this is your r in this direction, velocity is tangential. If you are in this direction, velocity is perpendicular to this in a circular motion, and your omega is coming out of the page. And in this view, it will be more clear that omega follows a right hand circular rule, and that v is omega cross r. So if your omega is in this direction, r is in this direction, v will follow this direction. The simple right hand thumb rule. So you may say the direction of omega will be, if you circulate a screw from v to r, you'll get omega. So v, omega, and r have a circular permutation. Omega to r, you get v, and a screw from, let's say, r to v, you get omega. So please always remember that. R this direction, v this direction, omega this direction. So that direction of omega will be very important when you deal in real life problem. We still didn't introduce force actually, but as you are a BSc physics student or MSc physics students, you know what a force is, and you're familiar with all of this, but just a brief recap. Let's say we have an outward radial force. Whenever a particle goes circular, we have an outer radial force. It is mv square by r, mv square by r, and it's written as also m omega square r, because as v equals to r omega, always satisfied by magnitude. So we are not writing vectors here. So it's just a simple radial outside force. Centripetal force, it is called. Whenever there is some curvature, it feels a outside force, outward force. So you do real life problem with this. So okay guys, so if something is rotating, the particle is facing a force outward. So okay, see, we have something more to discuss. All this should be bold format, otherwise fine. So as I have already shown you in the last slide, so your tangential displacement is ds. If you say this is ds, and I will call you this is r d phi, and tangential velocity, if your r is fixed, you know all of this, that ds dt is r d phi dt, and v is ds dt r omega. This all repetition of this itself. I just add one thing, it's a tangential acceleration, and that tangential acceleration will have okay guys, I got a SMS. So the only thing I added here is tangential acceleration. It's just dv dt, and if we do a dv dt, what I get, as omega is fixed in this constant, you just get sorry, not omega is fixed, absolutely sorry, r is fixed, so it's simply r d omega dt. This r alpha, it's called angular acceleration, if your omega is not constant. If your omega is also constant, r is also constant, this is called fixed angular velocity, and in that case angular acceleration is not there, and so tangential acceleration is also not there. We'll come across real life problems, so don't worry. Finally I get, I should this and corrections date. Here I tell you one more thing, that not only about r and theta, if any vector a is rotating and a, the magnitude of a is fixed, that a starts here and ends up here, magnitude is fixed, that is a rotating a vector. Here a position vector is rotating, here any vector a is rotating. The vector is rotating and the magnitude of that vector is constant. Modulus of a, which is the magnitude, of course. If you forgot, then please go to class 2. In this class 2 of this course, of course. So go to class 2 and see what the magnitudes of a vector is. So here we have a vector who is rotating, keeping its magnitude fixed. So for that vector, I can also prove by exact same argument that rate of change of that vector dA dt will be omega cross a. This is very, very important. Here you're doing the same thing, right? Here you're doing that dr dt is omega cross r by this geometric argument. By similar geometric argument, I keep this as a home task. by same geometrical argument, you please try to prove for any vector whose magnitude is fixed, please, and it's rotating by one point is fixed. Any rotating vector, this point is fixed. This point is fixed. So you may take this as origin. I should do a shape there. So don't worry about its feeling. It will be clear. Okay. So wait, maybe wait. Okay. So please try to prove this. Discuss with your friends. It's not that tough. Use this argument, similar argument. This will be important. Okay, we'll come across. So now I will give you a geometrical view of the centripetal acceleration. So, okay guys, a particle is rotating. So this is r, this is also r, this is d phi. So this is the direction of r. This is the direction of r plus delta r. So let me call this in bold format so that the vector nature is to be understood properly. So here also I should get all the bold. These are all vectors. Is my recording is on? Yes, on. So okay, I am insert by no. Fine. So if this is r, this is r plus delta r, so this is delta r. So we know that v is r omega. This is just repetition. For acceleration also, you see here this is r d phi in this direction. This is the velocity. No, this is r d phi. This is just the displacement. Velocity also, it's r omega. But what is the direction of velocity? The magnitude of velocity is fixed if your omega is constant. So now the direction of velocity is in this direction here. When the particle reaches here, the direction of velocity is in this direction. So if I say here is r and here is r plus delta r, so I will say here the velocity is v, and here velocity is v plus delta v. So this is v. This is v plus delta v. The direction, of course, this is the direction of v, this is direction of delta v. So here I saying it's a magnitude. So when omega is fixed, so I can easily say by using same argument that this is delta v is v delta phi, and delta v by delta t is v delta phi delta t, and it will be simply as v omega, and this will be omega square r. You please think what will be the direction of it. If the direction of r is this, r plus delta r is this, so your direction of velocity is in this direction. If your direction of velocity is this and v plus delta v is this, so the direction of acceleration will be towards the center. If this is the velocity, if I say this is, let's say, v plus delta v, so then you see that the direction is towards center. So I didn't want it to make this diagram messy, so just keep it projection. This is v plus delta v, So the acceleration, the direction of acceleration is simply towards the center. So up a bit. And this direction will be v plus delta v. Sorry, delta v, the direction of delta v is in this direction. So this is towards the center. So this is just a first geometrical view about the centripetal acceleration. This is not that tough, but if you are getting stuck with it, I would rather ask you to draw the diagrams. I alone cannot teach you everything. Yourself do the rest of the work. I just give you a path, that please proceed with this path and just think and do a diagram, and please try to understand that in this similar way I can construct a velocity diagram and understand the acceleration will be omega square r at the center. Okay guys, so we just ask you a question that when a particle moves in a circle with a uniform speed, you may pause this video right now. Whereas velocity and acceleration are both constant, or velocity is constant, acceleration changes, acceleration constant, velocity changes, or velocity and acceleration both change. So you may pause and think. Yes, you got it right. Both its velocity and acceleration changes. Particle moves in a circle at uniform speed. Its velocity changes. Acceleration how? The magnitude of acceleration does not change, but the direction of acceleration changes. If a particle is here, its acceleration omega square r in this direction, and if a particle is here, its acceleration is omega square r in this direction. So acceleration of course changes. It is the direction of acceleration which changes. Okay guys, okay, now I will construct one more very important construct, which is fixed point rotation about an axis. Please try to understand what's happening. A particle is fixed, sorry, a vector is rotating like this. How? Forget about all of this. I better increase myself here. Say, okay. So if this is fixed, better here. The particle keep rotating. The particle keep rotating like this. I'm changing the theta, but one point is fixed and it's rotating like this. It's more better. It will be better if I sorry. Myself a little bit smaller. Should I have something more? Okay, this works. This is very wide. The theta changes, but I think you got my point. So okay, I rather be myself very small in this diagram. Okay, or better if I move it a little bit here. So I guess now I can be more useful here. So let's see. So I guess you got the visualization. A danda, a rod is rotating like this. So its angular velocity is in this direction, above direction. So if the vector, that vector is a at in this initial position, the vector is a plus delta a in the next position. So I can say that your vector has increased or got an increment of delta a is in this direction. And as the whole point is, the whole discussion is like, oh, I don't get the shot. Okay. So. So as the particles, this position, the rod's position is fixed here. It's just rotate like this. So I can easily say that when the vector goes from a to a plus delta a, it goes delta phi angle. It traverses delta phi angle. So dA is the tangential direction of the dashed green circle, this delta A, and that delta A is the increment of the vector. So I can have a simple view of this, that theta is fixed, so it will make a cone. So dA dt is also in the tangential direction, of course, if your delta A is in this. So after delta A by delta t, as delta t is not a vector, so it is also in this direction, always tangential direction. So now you have an aerial view. What is an aerial view? You're observing from above. So if you're observing from above, you see that your A is here. So that, if this is your theta, so that projection, or better to say, this projection will be how much? This projection will be A sine theta. This projection. And if you get this projection, it will be simply A cos theta. So if you are doing a radial view, aerial view, so this is A sine theta, and when you traverse a bit, this is also A sine theta. That angle, I write it, this is at A sine theta, and of course this is also A sine theta, and that is delta phi. So that delta A is nothing but A sine theta delta phi. So that is the key line here. Now if you understand this, then everything is very simple. In aerial view, this is A sine theta in the first position, and when it goes to the second position, as it moves in a circle, your theta fixed, so the radius of the circle remains same, which is also A sine theta. So that delta phi is the angle. So that distance, when delta phi is very small, this is A sine theta delta phi, and that is of course the magnitude of delta A. That's why I'm just writing the magnitudes here. So delta A is A sine theta delta phi, just divided by delta t. So it will get you delta A by delta t. It's A sine theta delta phi by delta t. So I can write it as dA dt, as theta is very, as t is small. So it is omega, delta phi by delta t is omega. It's omega multiplied by A sine theta. It's very important. And in a vector, as vector, this will be as dA dt is omega cross A. It's a complete exercise. So if you tell me, sir, how do you get the cross product? You just think about it. What is the direction of delta A? This direction. What is the direction of omega? In this direction. What is the direction of A? In this direction. So omega to A, you get a screw, you get this direction of delta A. Think about the directions. How do you get, sir, that this will be a cross product? My intuition. Of course, all the three quantities are vectors. I got a match. Very sorry, I getting a little bit of sleepy. It's already 2 a.m. at night. Of course, since a month, very tough schedule. So I got analogies from all these discussions. All the discussions. You think about it. If you are getting stuck here, but how do sir get a cross product? No, I didn't prove that. I left this for you to think. See, I am not that kind of teacher who will just believe on spoon feeding. No. If you want to be a physicist, you need to think. At this point of time, you need to learn how to think. So please bother about it. Do. Okay. Now I get the main point, which is velocity in plane polar coordinate. Here we will write derivatives at dots. So I write dA dt as r dot, d theta dt as theta dot, d square dt square as r double dot, d square theta dt square as theta double dot. We start with my position vector, which is r hat as cos theta I hat plus sin theta j hat. Not position vector, I'm very sorry. I'm starting with r unit vector. So if I take a derivative of r unit vector, as you see, as I have already told you that r unit vector is not constant. Here, when the position is like this, r unit vector is here. When the position is this, then your r unit vector is in this direction. So mod of r unit r hat is 1, of course. The magnitudes are 1, but the direction changes. And as direction changes, of course, we'll get some dr cap dt. So, okay. I got a knee pain also. I don't know. Sometimes I feel that my age is becoming very high, but not that high. I am 35 plus. So, okay. So here, if I do take a derivative, what I get? I need to take derivative of both. So cos theta, but when I get derivative of di hat, it is 0. Why sir it's 0? Because I hat and j hat is fixed. I already told you that this is the direction of I hat and this is the direction of j hat, and they are fixed. The direction of I and j does not change. So this will be ddt of cos theta I hat plus ddt of sin theta j hat. I could just get a sin theta minus, of course. get a cos theta here, so I get minus sine theta I hat plus cos theta j hat and got a theta cap. How you, sorry, theta dot. How you get theta dot? d dt of cos theta. So sine theta, I believe you know, if you don't, d dt of cos theta, say this is called chain rule. d theta of sine theta, sorry, cos theta multiplied by d dt of theta. So that's how I get a theta dot. This comes. So here I get theta dot common. So this will be important. dr cap dt is minus sine theta I cap plus cos theta j cap multiplied by theta dot. What is this? This is theta cap. This is theta cap. So how did you get it? Please come back here or pause, go back in this diagram, and how did I explain this to you? By geometry and just vector projection. Think about it once again. So I get it here, I come back here once again. So this is theta cap. So your theta cap is minus sine theta I cap plus cos theta j cap. So dr cap dt is minus sine theta I cap plus cos theta j cap theta dot. This is theta dot theta cap. Similarly, if you get d theta dt, of course you have theta, sorry, d theta hat dt, your theta hat is this. So you get derivative of sine theta will be cos theta. So minus cos theta I cap. And cos theta's derivative will be sine theta. So minus sine theta j cap. And one theta dot comes from this chain rule. d dt of cos theta is d theta of cos theta into d theta dt. Similarly, in this theta dot comes. So it will be minus theta dot r cap. So we get very important result. dr cap dt, rate of change of unit vector in r direction, is theta dot, rate of change of angle, multiplied by theta cap. So dr cap dt is in the direction of theta cap. So rate of change of unit vector of r will be always in the direction of theta unit vector, theta cap. d theta dt also, we get it back, minus theta dot r cap. So rate of change of theta unit vector is in the direction of r unit vector multiplied by a minus theta dot. You do please remember this. We'll use it in the just very next part. So now it's time to do a velocity. So velocity is nothing but d dt of r cap. To do a derivative, we need to first derivative r, keep this r hat constant. Then I get r outside and get r hat constant, r hat derivative of r hat. So this is also the chain rule of derivative. So it's got r dot r hat plus this, and here we use this here. So we get this r dot r cap plus r theta dot theta cap. Got it? I guess you get it. So here I see that velocity have two components. One is radial velocity. This is the radial component, and this is tangential velocity. So this r dot is radial velocity, and this r theta dot is tangential velocity. Okay, so radial velocity theta is constant, r varies. In tangential velocity, r is constant, theta varies. So this is in a general sense, this is a special case. These two are special case. In a general case, we can have anything varies, anything. So if theta also changes, theta varies, the particle moving on. So in a complicated motion, both your r, theta, r, everything varies. So you can have both linear and tangential velocities. But this is the special case. Special case. So, okay, in a general motion, it would go on like this. How much time I already spent? 50 minutes. By similarly, I can, no, I should not be there. So similarly, I can derive the acceleration in plane polar coordinates. How write this? Okay. So this is not that tough. So you got your v velocity is this. So if you just get a derivative of this, you get r double dot r hat plus r dot dt. So you just keep derivative. This term is there, this term is there, secondly this term is there, ddt of this. Here you have three terms, so you get 3 r dot theta cap, then r theta double dot. I'm taking derivative, and finally I both r and theta dot constant, ddt of theta dot, sorry, theta hat. So we just use this. I use this here, and just you do a check. Please do a check. So please remember, this is important. This is very, very, very important. This is a general formula of acceleration. We have 4 terms there, 2 terms in radial, 2 terms in tangential. Here I got r double dot minus r theta dot square. Then we got r theta double dot plus 2 r dot theta dot. So this is tangential acceleration overall, the tangential component, and it is a radial component. There are the 4 terms. This is the most general way I can write acceleration, and we will have capital N number of Avogadro number of application of this. I may see myself so a little bit bigger. See, if I am that enthusiastic at night of 2:13, so it's 2 a.m. and 13 minutes. You also should have some energies. Okay, so let's move, keep myself smaller there. So you do, please do that derivation. You may pause here, go back here, or you go back here also. How did I do that derivation? You make a pause any point of time. That is the key. If you didn't understand this, you're not getting anything. So okay guys, come here. I did it. So we got the 4 terms. This is acceleration due to change in radial speed. This is actually the centripetal acceleration. This is the acceleration due to change in tangential speed, theta double dot. If your angular velocity is itself not a constant, it also changes. So this is acceleration due to change in tangential speed, and this is called Coriolis acceleration. We'll learn about later. So please remember this. Your velocity, the expression of velocity is this. The expression of acceleration is this. Okay. So then we have learned something. So horses are always a symbol of energy, symbol of triumph, symbol of determination. All positive vibes comes with horses. So sometimes we do the diagram of horses in our teaching. So let's see. Let's have an example. A particle moves with theta dot as omega, that is a constant, and r is r naught e to the power beta t. Should I delete for time being? Yeah. So that for certain values of beta, the particle moves with radial acceleration 0. Whenever I write r below a as a subscript, you should understand that it's radial acceleration. So think about it. You got theta dot as constant and r as a function of time. You may pause the video any point of time. R is r naught e to the power beta t. It's given as a function of time. So I need to show for certain values of beta, the particle moves with the AR is 0. Okay, now you get the solution. So I need to calculate the acceleration by using the general formula. So r as a function of t is given, and you ask something about the radial acceleration or tangential acceleration, directly use that formula. Directly use that. So just do a double derivative. Theta dot is omega, that is a constant. So theta double dot is 0. That means theta double dot is 0. Surely. So we just counted this. So now you can see that if beta is plus minus omega, after you come here, please make a pause and think. Beta is plus minus omega, then the radial part. This is the radial part. Vanishes. This is called AR. You'll get an assignment, a whole assignment, a set of, I think, 8 or 10 problems related with this. So another problem. IIT jam problem. Should I get it? Sure. A particle is moving in a plane with constant radial velocity. That means r dot, which is constant, is 12. And a constant angular velocity, theta dot, is 2. When the particle is at distance r equals to 8 meters from the origin, the magnitude of the instantaneous velocity. R dot is 12 given, theta dot is 2 given. When r is 8, the magnitude of instantaneous velocity. That means what you asked is mod of v. It's very simple. V is r dot r hat plus r theta dot. R dot is given, theta dot is given, and r is also given. Use this and do that. Very, 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 very simple, simple, simple. Very simple, simple, simple. Okay, guys, next what we have another problem. Here also I got it cut first. In planar polar coordinate, an object position at time t is given as r as a function of time, theta as a function of time. R as a function of time is given, theta as a function of time is given. It is asked about magnitude of its acceleration. It's very simple, isn't it? Very simple. Magnitude of its acceleration. So r as given and theta is also given. So is asked. You know what your A is. It's very simple. Your A is this. So R is this, R dot is this, theta dot is this, R double dot is this, theta double dot is 0. So at t equals to 0, R equals to 1, theta is 0, R dot is 1, theta dot is square root of 8, R double dot is 1, theta dot is 0. Substitute those values and then get this. It's very simple. Pause it and please do understand it. Yeah, we're almost over an hour. Yeah, so let's wrap up very first. I am more in increased position right now. Whenever I get something, some content here, I quickly get it smaller. So am I still there? I should be smaller. Okay. A very long rod rotates about a pivot like this. A bed is constant to slide along the rod without friction. A rod can rotate and a bed can move. At time t equals to 0, the bed at rest at a distance td away from the pivot. So this distance is d at t equals to 0. So its distance from the pivot at time t is, it's very simple, but slightly you need to think. What is the equation of motion? Still we didn't introduce Newton's law, but okay, I assume you know Newton's law, which is forces mass into acceleration. So here what is the force? The only force when this moves is force outside, m omega square r. I told you sometimes earlier that when something goes circular, we had some outward radial force, which is m omega square r. So m omega square r will be a force outside, and that should be m r double dot here. So use this. If you know how to solve a differential equation, then think about what will be the answer. This is called an initial condition. At t equals to 0, r is d, r dot is 0. So if you don't know how to solve a differential equation, then please take any basic mathematical physics book and try to find out where a differential equation is given. So r double dot means d square dt square. So it will be a very simple solution, exponential solution. This is second order linear differential equation. So the equation and motion maybe in a more familiar form is, let's say, omega square r. Omega is constant. That is constant. So now do a solution. Think about it and try to solve it. If you are not understanding, then you're not understanding what a differential equation is. So please do that as let's say this is your project work. So okay guys, I should tell you right now that you got an acceleration vector. You got an acceleration vector, a most general acceleration vector. So surely you will get a force, most general force vector. So that is this. So force is just nothing but acceleration multiplied by mass, as long as mass is constant. So mass, if mass is varies, also the force, the definition of force doesn't change. Well, but we add up forces dp dt, that doesn't change, but we'll add an extra term when we learn about variable masses. So we'll learn about variable mass. So, but okay, for the time being, for constant mass part, the mass is multiplied by acceleration. So this is force vector. Sometimes you need to come across those terms. So this is radial force, this is tangential force, a most general force vector in two-dimensional polar coordinates. Okay, yeah, we are almost at the end. Let's have this final example. So consider two particles moving along x-axis. In terms of their coordinate x1 and x2, the velocities are given. Let's this, but I got this above and just paste it. So two particles moving along x-axis. In terms of their coordinates, the velocities are given by dx1 dt is x2 minus x1, and dx2 by dt is x1 minus x2. That means dx1 by dt is negative of dx2 by dt. No problem. So these are equations of motion of both the particles are given. When they start moving from the initial locations of x1 equals to 0 and x1 at 0 is 1, initial position. Initially your x1 mean your first particle, two particles. This particle moves, this particle moves. The particles coordinates are given as x1. That means if a particle 1 is moving, its distance is called x1. Particle 2 is also moves. Particle 2 also moves. Its distance called x2. So their velocities are negative of each other. So this is positions of two different particles. Okay. So initial location, initially that was at first particle was at 1 and the second particle was at -1. So initially I can see my first particle and my second particle. The time dependence of both x1 and x2 contained a term in the form of e to the power at, where a is a constant. The value of a is. See, this problem has nothing to do about all what we have learned in this class, like velocity and acceleration and polar coordinates. This problem have absolutely no relation with that. Still, I wanted to do this problem at that end, because in this class we have come across differential equation 2 times. So if any student get little bit of enthusiasm about differential equation, then the study of this problem will be very beneficial to them. So that's why we are doing this problem here. Let's see. The method 1 is like this. This is very crude method, very basic method. If I understand that x2 minus x1 and x1 minus x2, they are just a negative. So my dx1 at dt, it will be, let's say this is as z. So let x1 minus x2 as z. So dx1 by dt is minus z. And dx2 by dt is z. You just think about that. dx1 by dt is x2 minus x1, and dx2 by dt is x1 minus x2. So if this is z, this is minus z, and this is z. Then I just subtract this two equation. So it becomes gdt of x1 minus x2 is minus 2z, and this is dz dt is minus 2z. That means your z will be a e to the power minus 2t plus b. x1 minus x2 will be a e to the power minus 2t plus b. That means the time dependence of both x1 and x2 contained a term of the form e to the power at. Both x1 and x2 has a common term which is e to the power minus 2t. The value of a will be minus 2. Do I see my face? Is it good? I guess you got it. Some of you get it. It's called first order differential equation. By doing just +2 level of mathematics, we get that answer. But there is a general way. See, these equations are called because in other equation these terms relations may not be that simple, and that substitution of z may not work. So there is another method which is called a general method. First order coupled differential equations. So we can have 10 hours of discussion about it, but it will be very brief. Whenever you got a coupled differential equation, say this is some constant c1, c2, c3, c4, dx1 dt and dx2 dt, a combination of x1 and x2. Say it have a ca1 x1, c2 x2, c3 x1, c4 x2. We just write this as with all the coefficients, x1 dot, x2 dot, matrix. It's a matrix form. So always I do a handwriting, so sometimes do a matrix form. So now what we need is we need to find the eigenvalues of that matrix. We got the eigenvalues. The eigenvalues is -2 and 0. And the general solutions will be x1, x2 is c1, e to the power minus 2t, one eigenvalue. Another eigenvalue is 0. So that will be a general solution. And here, there will be the eigenvectors of this. I absolutely believe that no one is getting what is happening there. That's why I use this symbol. But okay, we'll come across this. We'll come back at some point of time. But this is a general structure of a coupled first order differential equation. Think what is happening. You have a coupled differential equation, first order. The constants, I write the constants as matrix. Here the constants are very easy. So it may be 2, 3, 4, 5, anything else here in the constants. So we will write every time a matrix with these constants, do a eigenvalue calculation. That eigenvalues will come as e to the power minus, sorry, not minus, whatever the values will be there. So e to the power lambda 1t, e to the power lambda 2t, and we got an eigenvalues, sorry, c1 and c2 will be constant, eigenvectors there, eigenvalues there. Should I get a little bit generalization? I think I should do. So if you have dx1 dt is c1 x1 plus c2 x2, dx2 dt is c3 x1 c4 x2, so that matrix will be c1 c2 c3 c4. Find eigenvalues and eigenvectors of this matrix. After you get it, general solution will be like this: x1 x2, it's some constant, let's say a, e to the power, eigenvalues are, let's say, lambda 1 and lambda 2, so e to the power lambda 1t, another eigenvector lambda 2t. Will come across, will come again. So eigenvector of lambda 1, eigenvector of lambda 2. If you does not know, then don't worry anything about you may know, you may don't know anything about eigenvalues and eigenvectors. So if you don't, please skip that. Please focus on this trick, and this is also a good trick. It will be used many a times. Those who know eigenvalues and eigenvector try to understand what I did it here, and then what I wrote here is a pro forma of general solution. So how much time? We are 1 hour 17 minutes already there. So we end this class with this example. So at the next class will be a little bit briefer. So 30 minutes or 40 minutes, we will learn about coordinate transformation, vector transformation, and rotation matrix. Once again, that matrix comes, always matrix comes. The whole world is a matrix, whole universe is a matrix. So, okay, please watch the movie Matrix. We have trilogy, 3 movies. So we do this. Finally, once again, if I come across this, I would request you to please subscribe this course for very simple payment, very generous payment. Okay, friends, you can any point of time can contact me in any of this communication channels. Finally, thank you. Thank you all who have watched, and my energy and dedications have make you a little bit of interested in physics. That is okay. That is my reward. Thank you very much. And then see you in the next class. Okay.